Go ahead, James.
Okay, thanks, Peter. As you can see, this is joint work with Carolyn Chen and Kristen Wetzler. This work started when Kristen was one of my graduate students at LSU, and I thought I would get started with something that would enable you to speak. So I'm going to start with the founding fathers of Matroid theory. And I want graduate students to answer this because if you're a senior person in Matroid theory, you should know this. So some pictures. Okay. Try again. There you go. Who's that? Unmute yourself and tell me who that is.
Henry?
No. Wrote the first paper in Matroid theory in 1935.
Whitney?
That's Whitney it is. Okay, second one. That one is Tutte. Yep, that was taken from the Bletchley Park website. Third one. Had a famous conjecture. Yes, Rota. And Oxford mathematician. Well, you should know who that is. Okay, so that's Dominic Welsh. Okay, so you've got a graph. It's got no odd cycles. Well, of course, you know that means that the graph is bipartite. So here's a graph result. I'd like to get a Matroid analog of it. Is there a Matroid analog of this? Does it have a Matroid analog in general? Well, the answer to that is no. But for binary Matroids, the answer is yes. So let's see how to do this. I've got a Matroid. It's binary if and only if what? Excluded minor characterization.
U24?
Yeah, U24. Okay, there's another excluded minor there's another characterization of binary Matroids in terms of the behavior of circuits. Two circuits. What about
the symmetric difference?
Symmetric difference is?
The union of circuits.
Yeah, disjoint union of circuits. Good, okay. And there's one about the intersection of circuits and co-circuits.
It's not odd.
No, even.
Yeah, it's not odd.
It's not odd, yes, indeed. So every circuit, co-circuit intersection is even. So if I take a binary Matroid, which is a disjoint union of co-circuits, then all of the circuits are even because every circuit, co-circuit intersection is even. Now look, if I go too fast or if I say something you don't understand, please interrupt me because I'm happy to try to explain it further. Okay, so binary, disjoint union of co-circuits, all the circuits are even. Okay, now let me think about a converse of this. So I'm going to start with a binary Matroid in which all the circuits are even. Here's a nice representation for it. What I claim is, with all the circuits being even, I can append a row of all ones to this and not change the Matroid. And that's because all the circuits are even. Okay? Now, so a binary Matroid with no odd circuits means that you've got a representation like this. Okay, so think about the R+1 dimensional vector space here. What I've done from that R+1 dimensional vector space is that I've removed a hyperplane. The hyperplane where the first coordinate is 0. Okay, so now I've got a vector space minus a hyperplane, or if you like, in this case, the binary projective geometry minus a hyperplane. projective geometry, take away a hyperplane is?
An affine geometry.
An affine geometry, indeed, that's what it is. So, if you've got all the circuits being even in a binary matroid, the simplification of that binary matroid is a restriction of an affine geometry. Okay, so let's look at these two results that I've got. Disjoint union of co-circuits means all the circuits are even. And if all the circuits are even, the simplification of the matroid is a restriction of a binary affine geometry. Okay, this being a restriction of a binary affine geometry, I'm going to give that a name. I'm going to call that affine. So I'll also add the condition the matroid is loopless. So a binary matroid's affine if it's a restriction of an affine geometry, or if its simplification is a restriction of a binary affine geometry. And of course the thing's loopless. Okay, so this is a theorem that's a combination of some results, one proved by Dominic Welsh and the other one proved by Tom Brolowski and Andrew Heron 50 years ago, essentially. So, disjoint union of co-circuits, if and only if all the circuits are even, if and only if the thing is affine. Now, we did 1 implies 2, and we did 2 implies 3. So if you haven't seen this stuff before, you could try 3 implies 1 if you get bored with what I have to say. So questions about that? The nice thing now is that we had this result for graphs. Oh, here's Dominic Welsh, relaxing. Okay, we had this result for graphs. No odd cycles means the graph is bipartite. For binary matroids, no odd circuits means the matroid is affine. So remember that. Bipart is to graph as affine is to binary matroid, because that's going to come up over and over again in what I have to say today. All right, so that's what the situation is if there are no odd circuits. What happens if I start to allow some odd circuits? And in particular, I'm going to allow odd circuits of size 3. I'm going to allow triangles. Well, this result of Maffray was the result that really started this work. We're going to add the condition that the graph is two connected and simple because it just makes it easier to state the result. Okay, so you can sort of predict what this result might say. Two connected simple graph, no odd cycles of length greater than 3, if and only if. Well, okay, so what's one class of structures? Is there anybody out there? No odd cycles at all means bipartite. What else? It might be small, right? It might be K4. What about a triangle or K4 take away an edge? Why haven't I listed those? Well, that's because they both occur as part of this infinite family. So what you've got here is clearly a bunch of triangles glued together across a single edge. Okay, so that's the situation for simple graphs that are two connected and have no odd cycles of length bigger than 3. Now this result, when I saw this result, I said, this has got to go to binary matroids. And we can do it in just exactly the way that you would expect. So you see bipartite there and you say, oh yeah, I know what bipartite means. And this is a result that Kristen Wetzler and I proved in 2016. We know what bipartite corresponds to. It goes to affine, okay? Now for K4 is telling us that the thing could be small, okay? So if I go to binary matroids, the rank wants to be small, so it won't just be K4, it'll be K4 plus Any ideas?
Fano.
Fano. Yep. Fano, indeed. So it's K4 plus Fano. And then this infinite family doesn't get added to. All you do is you allow the cycle matroids of these graphs. So this is a really nice, clean analog of a graph result. And the proof isn't hard at all. All right, we're going to be a bit bolder now. We're going to start allowing 5-element circuits. And Kristen did this in her PhD thesis, the result for 3 connected simple graphs. And we add this connectivity condition really to make the statements of these results cleaner. You can get the result for graphs in general, but the results statements are just messier. Okay, so we can have bipartite graphs, no odd cycles of size bigger than 5. Well, maybe if the graph is too small, like the number of vertices is at most 6. What else? Okay, so when we allowed triangles, what we got was a bunch of triangles glued together across a K2. Okay. So that suggests a bunch of K4s glued together across a common triangle. And that's what you get. That's the theorem. I've said you can delete at least 2 edges of the joined triangle. You can, of course, delete all 3 edges of the joined triangle, but if you do that, you just get back to a bipartite graph. Okay, so now we've got a graph result, and we sort of know how to generalize these results now. And this is the new result that we finally got a proof of. So this is the joint result with Carolyn and with Kristen. The analog of bipartite is affine. Number of vertices less than or equal to 6. So that's small rank. Okay. The rank is at most 5. You're certainly not going to have an odd circuit of size bigger than 5. Gluing copies of K4 across a common triangle. Now, before we saw that if you're going to have K4 in there, it should be maybe K4 or Fano. Okay, so we'll glue together a bunch of copies of K4 or Fano across a common triangle and then delete up to 2 elements of the joined triangle. And that's what you get. And for a while we thought that was all you got. Unfortunately, there are some small examples. There are 9 things that are sporadic of rank 6. They turn out all to be non-regular. So that's the main theorem. That's what I really wanted to talk about. And now we get to the point where, okay, you've said your main result, and the rest of the talk's going to be about proofs, and I don't really like listening to proofs. You should listen to this proof. It's got some really nice results in it, not my results, results that other people have proved, which I've only just learnt the value of. So I recommend at least listening to part of this proof. So here's the theorem. This is just a picture of what happens where you've got all these copies of the Fano glued together. Each time you add a new copy of the Fano, you raise the rank. So any questions about this to this point?
Hi, James. Quick
Dylan,
question.
hi.
In your 2016 result, that's a result for connected matroids, but so shouldn't you have things like 2 sums of Fano planes?
Yeah, but this theorem is for 3 connected.
Right, the earlier result, just with binary matroids of no circuits, odd circuits larger than 3, that's also for 3 connected?
Oh, Dylan, you're not going to ask me about a result that was published in 2016.
Sorry about that. I think your slide said 2 connected.
Won't two sums of Fano planes have 5-element circuits?
Yeah, they do.
Okay.
They do, because what you've got is a 4-circuit with a triangle glued onto it.
Right. So no further examples arise because of 2 sums.
No, that's what a theorem is, Dylan. Oh, sorry, I was supposed to be on my best behaviour, but you see, it couldn't last for very long. No, I think the theorem is right. Okay, I do think the theorem is right. You could question this theorem because we haven't even completely finished writing the proof. We're close, but we haven't completely done it. But I think the other one is okay.
Okay, thank you, James.
Okay, any other questions? You can see how kindly I deal with questioners. They sort of need months of therapy after speaking to me. Okay, so now we've got the theorem. That was an extension of the result to binary matroids. What about if you try to extend it to graphs with larger connectivity? And this was the main result of Kristen's PhD thesis. So I'm slightly changing the hypotheses from before. I'm going to tell you that you've got a 2t minus 1 cycle, a cycle of length 2t minus 1, but you've got no larger odd cycles. Well, now, what do you think? Well, of course, one thing you can get is that the number of vertices might be small. Okay? And now you've seen what the result is when t is 2 and what the result is when t is equal to 3. So you ought to be able to guess what the general result is. And here's the picture. Again, this picture that I keep using. So this time you start with a KTN. You have at least one edge on the t side. That's to get you your cycle of length 2t minus 1. And then you can put as many edges as you like on that side. Now, you look at this graph result and you say, how do you prove a result like this? What theorem would you like to use to prove a result like this? No graph theorists. Okay. We've got to prove it. This is a beautiful mountain. We've got to climb this mountain by proving the result. All right, so here's our theorem. If and only if. Okay. No odd circuits of size bigger than 5. If it's affine, it's got no odd circuits, period. If the rank is less than or equal to 5, it's got no odd circuits of size bigger than 5. If you glue together a bunch of copies of the Fano, as I've done here, you can check that you have no odd circuits of size bigger than 5. All you can really do is to get a circuit, is to use 2 of the pages. You can't use 3 of the pages. Okay. And this uses Sage to prove the last part. Okay. How do you do the converse? Well, I'm going to make a bunch of obvious assumptions. 3 connected binary matroid. I've got a 5-element circuit. The rank is at least 6. And I've got no odd circuit of size bigger than 5. So those are all obvious assumptions. The next assumption is one that really turns out to be useful. It's a minimality assumption. I'm going to assume that every time you delete an element in the matroid, but not in this 5 circuit, you lose 3 connectivity. Now, suppose I give you a 3-connected graph and I tell you every time I delete an edge, I lose 3 connectivity. What can you tell me about that graph? This is the result of Helene from 1969. Anybody know this? You know this one, Peter? Okay. If you've got a graph which is 3 connected and every time you delete an edge, you lose 3 connectivity, it's got lots of vertices of degree 3. And the Matroid analog of this, which was proved by Pak Ken Wong, is that you have a triad. That result was extended by Manuel Lemos, and we need that, or we use that in what we've got here. So we've got our 5-element circuit, and we've got a triad that avoids it. Okay. So think in the graph case, I've got a triad, so think of a vertex of degree 3 and a 5-element circuit. So this kind of picture. These curved edges correspond to paths. Now you can see that in the graph case, what would happen is that the lengths of these paths have to be pretty constrained. If I'm trying to avoid an odd cycle of length greater than 5, these paths better not be too long. Okay. So Menger's theorem is what you need in the graph case, and Menger's theorem for matroids is what you need in the Matroid case for binary matroids. So I want to get something that'll deal with a situation like this. Is there a Menger's theorem for matroids? Yes. Tutte proved this in 1965. This is a little piece of a picture of Tutte that I took in 1995. Now, I looked at this paper of Tutte, and I remember, for some reason it stuck in my mind, that I looked at this paper in the library, the mathematics department of the University of North Carolina, around 1978, 79, 80. And I didn't understand it. I had no clue about what it was saying. And one of the reasons I like this new theorem is that I've finally found a place to use this really beautiful theorem. Now, Jim and Jeff and Bert understood the significance of this result a long time ago, and they extended it. Took me much longer to catch on to it, but I think at least we've got a nice application of it in this particular case. So this is a really beautiful theorem. Many of you will know that Jim used to be a vegetarian. This is a proof that he is no longer. At least he wasn't for a while. Okay, so Menger's theorem. Menger's theorem for matroids, it's also called Tutte's linking theorem. Let's apply it in this particular case. So I'm in a 3-connected matroid. I've got a 5-element circuit, and I've got a disjoint triad. What Menger's theorem will give you is that you've got a minor whose ground set consists of the 5-element circuit and the elements of the triad. And the structure, the restriction of the minor to the 5-element circuit is still a 5-element circuit. And the restriction to the triad is the same as the restriction in M of the triad. Now think for a moment, when I restrict to a 5-element circuit, I still have a 5-element circuit. But the triad's a triad in the matroid. What sort of a set, when I restrict to the triad, what sort of a set am I going to get in a binary matroid? Can you see that I have to get an independent set? If I had a 3-element circuit and a 3-element co-circuit overlapping, I'd have an odd intersection. I wouldn't be binary. Okay, so this restriction to the triad, this is just telling me that the triad's an independent set. in this minor n. What else do I know about the minor? Well, I have this rank condition. Now, this is really a connectivity condition. It's telling me that the connectivity between the 5-element circuit and the triad is the same in the minor as it was in the original Matroid. Let's see what that tells us about the rank of the Matroid. Well, okay, the 5-element circuit has something of rank, has rank 4, and we said that the triad had rank 3 because it was an independent set. So the rank of the Matroid is 5. Now, I've already warned you that the triad is not necessarily a triad of the minor. But having warned you about that, now I'm going to show you that it actually is a triad of the minor. Because this triad of the original Matroid becomes a disjoint union of co-circuits in the minor. Okay, think about what happens when you do contraction, particularly in a binary Matroid, to a circuit, and you'll see that this is what happens to the co-circuits. So I've got a disjoint union of co-circuits. That's what T star is. But wait a minute. C's got rank 4, and N has rank 5. So that means T star is actually a triad. So some of that maybe I went too fast through. So let me just summarize what I've got. I've got this minor. It's an 8-element ground set consisting of the 5-element circuit and a triad, and the whole Matroid has rank 5. Now, we like drawing pictures of Matroids. If the thing's got rank 5, it's going to be hard for me to draw a picture of it. How can I draw a picture of it?
Try a graph.
Draw a graph?
Yeah.
Yeah, maybe, but what's the standard thing that we do? I've got an 8-element Matroid of rank 5.
Dualize it.
Yes, you dualize it. So the dual has got rank 3. It's got a 5-element co-circuit and a disjoint triangle. And I've got this rank condition. This is really a connectivity condition between the circuit and the triad. And this is a statement about the duality function. If you know about duality functions, you know that they behave the same under duality. I said duality function, I meant connectivity function. The connectivity function of the dual Matroid is the same as the connectivity function of the original Matroid. So what this is really telling me is that the 5-element co-circuit cannot all be clustered on a line. So I've got a rank 3 binary Matroid with a triangle and a disjoint co-circuit. I get one of these 3 structures. The co-circuit is 1, 2, 3, 4, 5, and the triad is X, Y, Z. Okay. This is what I have in N star. N star looks like one of these 3 situations. N star has got a collection of circuits and co-circuits. Where do these guys come from, the circuits and co-circuits of N star? Well, every circuit or co-circuit of N star is a subset of a circuit or co-circuit of M star. And I know that M star has no co-circuits of size bigger than or equal to 7. So that limits, that enables me to deduce some structure about this restriction N. Before I talk to you about that, I want to just talk to you about a convenient way of talking about a single element extension of a graphic matroid. These are called grafts. Most of you will probably know them. They were introduced by Paul Seymour. Here's the vertex edge incidence matrix of K4. Okay, so I've got all 4 tuples with exactly 2 ones. Let me add the column of all ones. What matroid is this now?
Fano.
It is indeed Fano. And I'd like to represent this as a graph. And I can do that by, I've got this hyperedge marked in red, and I'm just going to take a vertex, each vertex that corresponds to this hyperedge, I'm going to put a box around it. So this picture, this graphed picture, is a graph with a hyperedge. That's how you want to think about it. And I need that to represent some of the structures that can arise. There are 7 of them. So one of these structures is guaranteed to occur as a restriction of my matroid M. And I get that from those 3 pictures that I had earlier. Okay, so here are the pictures. These are all graphs. The top 5 are graphs. These ones here at the bottom are grafts. So this vertex, this vertex, this vertex, and this vertex is those 4 vertices which have boxes around them. They correspond to the hyperedge. Okay, X, Y, Z, that's been circled. That's clearly a triad in this restriction. It's also a triad in the original matroid. Okay, so I've got this much structure for the matroid. Getting a second triad turns out to be really useful. This is Broad Beach in Australia, which is surface paradise. So we've got these 7 choices for the restriction of M to Z. We want to get a second triad. You get that unless this M restricted to Z spans the matroid. So we had the rank as at least 6, and now I look at my pictures. M restricted to Z spans the matroid and the rank is at least 6. So now I look at the ranks of these things. These are just graphed pictures. Okay, this guy has got rank what? It's got 6 vertices. Looks to me like the rank is 5.
Rank 5.
This is rank 5. This one's also rank 5. This one is rank 5. This is rank 6. Rank, what? 7, 7, 6. Okay, so I only care about it's only these ones on the right wing that give me trouble. There are only 4 choices, H2, H3, H5, and H7. When this M restricted to Z spans M, I only get the things of rank 6, and there turn out to be 9 matroids like this, and the number of elements is 9, 10, or 11. Now, this is done using Sage. Now, those of you who know anything at all about my competency with the computer will know that I did not do this. So my co-authors took care of this part. Okay, so we get these sporadic examples. There are 9 of them. They're all non-regular. Okay, a second triad. That's the case that turns out to be where there's a lot of case analysis. So I've got one of these 7 structures. and I get another triad, which I'm going to call STU, which is disjoint from the ground set of one of these structures. There's no overlap there. So I've got this triad STU and a 5-element circuit, 1, 2, 3, 4, 5, and a triad XYZ and a circuit 1, 2, 3, 4, 5. And the triad also relates to the 5-element circuit in exactly the same way as the original triad did. So I get one of these 7 cases. So you can see this case analysis and 7 cases for the first type and another 7 here. So this looks like 49 cases. It's a little bit worse than that because, well, here we always concentrated on using the same initial 5-element circuit. We actually need to notice in some of the cases that, for example, there's another 5-element circuit here. And we might have to move to a different 5-element circuit to make this argument finish off. But anyway, we can do it. So we made that minimality assumption. We had all of these natural assumptions, and then we had this minimality assumption. And the proof that we've done up until now relies on this minimality assumption. And it turns out that what you prove, subject to this minimality assumption, is that the structure that you get is this graph guy. It's all of these K4s glued together across a common triangle where you can take one or two of the edges of the triangle away. So I'd like to drop this minimality assumption. What extra do I get? Remember, I've got to make sure that I don't wind up with an odd circuit of size bigger than 5. Well, we know something that we get, and it turns out that that's all we get. You can glue, instead of gluing K4s across a common triangle, you can glue Fano's across a common triangle. And sometimes you might have a K4 and sometimes a Fano. That's fine. But there's nothing else that you can do without creating an odd circuit of size bigger than 5. So questions about that? Okay. We did this result for graphs initially, and we were excluding cycles of length greater than 5. So we could do it for co-graphic matroids, and then we'd be excluding bonds of size greater than 5. But that would mean needing to remember what the dual of a bipartite was. What's the dual of bipartite? Okay.
Eulerian?
It's Eulerian indeed. So when we apply the result to co-graphic matroids, 3-connected simple graph has no odd bonds of size bigger than 5, if and only if the graph is Eulerian or it's tiny. Number of edges is the most, the number of vertices plus 4, and the number of vertices is at most 8. So that just follows straight away from the Matroid result. Okay, so let me summarize. We started off with this result of Borowski and Heron. Binary Matroid has no odd circuits, if and only if it's affine. If I allow triangles, well, I get affine or I get small, or I get copies of K3 glued together across a common element. And now if I go to 3 connected, I get affine or small, or copies of K4 or Fano glued together across a common triangle, or these sporadic things, of which there are 6. So that's the binary matroid result. And then this is the graph result. This now works for arbitrary t bigger than or equal to 2. You've got an odd cycle of length 2t minus 1, but no larger one. Then the graph is small, or you get it by gluing together across a kt a bunch of copies of kt plus 1. And I'm going to finish with a picture that will remind you that there are beautiful things in the world when we eventually get out there to be able to see them again. This is Wineglass Bay, which is on the Freycinet Peninsula in Tasmania. So thank you for your attention.
All right, thanks very much, James. I don't know how to do applause. Let's hold down spacebar and applaud. I still applaud with one. Are there any questions?
Yeah, so I guess I could ask the obvious question. Is there something like this Wetzler result, but for binary matroids in general, or at least for co-graphic matroids?
Yeah, that's a good question. We haven't tried it for co-graphic. That's what we're working on at the moment. We're trying to do it for connectivity bigger than 3. One of the results that we relied on heavily was this minimality result, which guarantees the existence of a small co-circuit, in this case a triad. It turns out that if you go to 4 connected, then you do have the existence of a 4-element co-circuit. That was proved by James Reed and Haidong Wu and Zhou Zhou. But that result is not known for bigger than 4, where the rank is, where the connectivity is bigger than 4. So that would need to be overcome. I mean, the answer should be that what you do is you take a bunch of projective geometries, let's say of rank t plus 1, and you glue them all together across a projective geometry of rank t.
Right.
So that's what the answer should be, provided the rank is big enough. In general, you're probably not going to be able to work out what the small, I mean, there are going to be some small rank things which are going to be tricky to get in general. But that's what the answer should be. We had a lot of trouble doing it in the 3 case. It was a lot of work in the 3 case. So it's going to be work to get it, I think.
I was just wondering about a qualitative kind of result, but I think that I seem to recall talking to Peter about this in Louisiana last year. So the one case, those things with the planes coming off, that stops you having long circuits.
Yes.
So if I've got a connected binary matroid and it's got a long circuit but no long odd circuits, what does that say about the structure? Do you remember anything? Do you know anything about that?
I think it, from my vague memory of this conversation, it turns out that it's small in some sense. Like that's it.
Okay, so if you've got an odd circuit but you don't have any
Big odd circuit.
if you have a binary matroid with a long circuit, then it has to have a long odd circuit as long as it's got one. As long as it's got an odd circuit, it has to have a long odd circuit. So there's a qualitative thing, because we understand what binary matroids are that don't have long circuits.
Yes. Okay, so we haven't done that. But that's a good question.
I think we talked about getting an upper bound on circuit length. So if you have connectivity and you have an odd circuit, and you know you have no long odd circuit, then you can get an upper bound on the circuit
A factor of 2.
size.
Isn't there a width parameter that's bounded if you don't have long circuits? I can't remember.
Yeah, it's even more than that. We have a very good description because there's this. Basically, there's a theorem of CMOS that if you contract the longest odd circuit, then in every. So if I got a connected matroid and I contract the longest odd circuit, then. I can contract the longest circuit,
Yeah.
then the size of the longest circuit goes down, and so you repeat that in the components.
Yeah.
So you get this tree-like structure from that. So we have a very precise understanding of the structure, not precise, but a pretty good understanding of the structure of binary matroids without long circuits. And my recollection, but I don't remember the details, is that the size of the longest circuits bounded by a factor of 2. If you bound the odd circuit and you're not affine, then there's no long odd circuits within a factor of 2 of what you're looking for. But I don't remember the details.
Okay.
Are there any other questions? Well, I won't attempt to get us to thank James again, but thank you, James again. I guess a couple of housekeeping points. So for those of you that got here from the blog, there was a somewhat cryptic hint to the password on the blog. The password is always going to be the speaker's last name in lowercase, followed by the digit 1. That's so it's going to change every week, but it's predictable from the speaker, and we're not putting out information on the blog to stop scurrilous people doing bad things. And so I won't send out any more emails, but if you'd like to subscribe to the Matroid Union blog, then all the talk announcements will be made available there, and feel free to tell your friends, of course. Yeah, I think that's it. If we'd like to have a discussion now the talk is over, one thing I can try to do is breakout rooms, so I can put people in individual rooms to have group discussions. Probably 80 people is a bit much. So send me a message via Zoom if you'd like to be put into a breakout room. Otherwise, thanks everyone for coming. It's great to have such a great attendance, and thank you for people in uncivilized time zones at the moment, especially, which is half of the world.
Thank you.
Peter, a quick question. You've definitely settled on a time for the next talk?
Oh, sorry. Yes, I did mean to say that. So the next talk is Dylan. I think we've settled that we're not actually doing this time next week. So this clashes with a graph theory seminar at Princeton, or the Princeton Combinatorics seminar, and we'd like to avoid that clash. So we're looking at another time, but I can't confirm anything. But it won't be exactly a week from now. But there'll be more information on the blog soon.
Thank you.